We are happy to present our work generating part-aware editable 3D shapes without 3D supervision. Our main interest lies in generating part-aware 3D shapes, but why do we really need parts? Let's imagine a shape editing scenario where a user needs to make local changes to the shape and appearance of different regions of an object, such as applying rigid and non-rigid transformations on specific areas of the object, changing the appearance of a part, mixing and matching parts from different objects to form new objects. It is clear that parts are essential when local control is required. Existing NeRF-based generative models are able to extract high-quality 3D meshes while only requiring 2D supervision. However, they do not offer explicit part-level control. Current part-based generative models enable explicit part-level control, but require 3D supervision in the form of occupancy labels and aren't capable of generating texture. We propose PartNeRF, the first 3D part-aware generative method that can perform local shape and appearance edits and only requires post-2D images and object masks during training. Our approach is based on the seminal work of neural radiance fields. Neural radiance fields map a 3D point x and a viewing direction d to a color value c and a volume density value sigma. During training, different views of the same object with known camera poses are provided. The network learns the geometry and color of the object using multi-view consistency. To render a novel view, multiple points are sampled along the ray of a corresponding pixel, and the rendered color is calculated by volumetric rendering, using the predicted density and color values. The volumetric rendering equation can also be reformulated to directly use occupancy values instead of density values. We introduce PartNeRF, a method that decomposes a 3D object into m parts, each being parameterized as a neural radiance field. Each part consists of an affine transformation that maps a point x to the local coordinate system of the part, where Tm is a translation vector and Rm is a rotation matrix. The part is also augmented with a scale vector Sm that defines the spatial extent of each part, and two latent codes that control the shape and texture of the object. We employ two separate networks, a color network and an occupancy network, that are conditioned on the two latent codes and are responsible for extracting the occupancy and color values for each point and individually per part. As we are interested in performing local edits, our parts need to span across local and continuous regions. In order to achieve this, we multiply the predicted occupancy function with an axis-aligned 3D ellipsoid occupancy function. We adapt the volumetric rendering equation of NeRF to a per-part rendering equation where for each ray we render a different color value for every part. To ensure distinct manipulable parts, we enforce a hard assignment between rays and parts. Specifically, we associate a ray only with the first part that it intersects. In order to achieve this, for each ray we retrieve the index of the first point that lies inside each part using the function psi. Then, we define the associated rays to the mth part as the rays that first intersect with that part. The rendering equation for the entire object becomes a function of the hard assignment, as the color for array R is only rendered using the associated part occupancy and color predictions. Note that when an array is not associated with any part, it is rendered as the background color. We now discuss the PartNeRF architecture and how we can generate 3D objects using our method. As input, we are given a collection of 2D images and object masks along with their respective camera poses. We train a separate model for each semantic category. Our model is based on the autodecoder architecture. To generate a 3D object, we sample a separate shape and texture code ZS and ZT and feed them to the decomposition network. This network maps the shape and texture codes to m per part shape and texture codes respectively. Given a per part shape code, the structure network predicts the pose and scale for that part. To generate the novel view rendering, we first sample points along rays and transform them using the pose and scale predictions. Then, the neural rendering module takes as inputs the transformed points, directions, and per part latent codes, and predicts the per part color and occupancy values for the sampled points. We use volumetric rendering to extract the per part rendering using the predicted occupancy and color values. We follow the same procedure for all m parts and compose the per part renderings all together, resulting in a generated rendered image. During training, we supervise our model using an objective function that is composed of 6 terms and 2 regularizers. We use a reconstruction loss that enforces the rendered and the ground truth image colors to be the same, and a mask loss that ensures that the rendered and ground truth mask values match. The occupancy loss further refines the object boundaries and is crucial for the hard ray part assignment. We also introduce a set of losses that guide our network to learn editable parts. The coverage loss distributes the parts along the object. The overlapping loss forces non-overlapping parts. Finally, we impose a control loss to decompose objects into equally sized parts for better editing control. The L2 regularization applied to the shape and texture codes is used to constrain the latent codes within the normal distribution, following other autodecoder-based methods. We compare our method with NeRF-based and part-based 3D generative methods on ShapeNet categories. We measure the minimum matching distance and the coverage metrics to showcase the generative capabilities of our method. First, we compare with several NeRF-based approaches and achieve better or on par results when comparing with volumetric rendering-based approaches. Note that these methods do not consider parts and do not allow any part-level shape editing operations. The results shown here are reported for the chair category and the car category. We also compare with part-based 3D generative methods that require explicit 3D supervision during training. We showcase better performance on the airplane category and on par performance on the table category, while not requiring 3D supervision during training. For more quantitative and qualitative comparisons, please refer to the main paper and the supplementary material. Let's now look at the capabilities of our method. First, we train our network on the LEGO dataset of NeRF and showcase scene-specific edits. Here, we render novel views of the reconstructed original and edited LEGO tractor. Our model is capable of doing editing operations like lowering the bucket of the tractor, removing the cockpit and placing it on the floor, resizing the cockpit to be larger or smaller, and colorizing the bucket. All these operations are possible by directly selecting and editing the PartNeRF parts. The part decomposition of our method enables shape mixing of two or more objects. Here, we showcase shape mixing on ShapeNet categories. We select parts from the first shape and parts from the second shape, highlighted in green. We perform shape mixing, where we only mix the per part shape codes and keep the per part texture codes of the first object. Then, we perform texture mixing, keeping the per part shape codes of the first object and only mixing the per part texture codes. Finally, we showcase mixing of both shapes per part shape and texture latent codes. We also present shape mixing examples on the airplanes category. PartNeRF can perform several shape editing operations on the ShapeNet categories. A user can select parts and perform translations, rotations, and scaling operations, as well as per part texture editing operations like colorization. Finally, we show some examples of generated 3D objects using PartNeRF. For more results, please check our paper and supplementary material. To sum up, we presented PartNeRF, the first part-aware generative model that parameterizes parts as NeRFs. Our model enables part-level control and numerous editing capabilities with no need of explicit 3D supervision. Our work has two limitations. Firstly, the texture quality of our method could be improved by considering other adversarial losses or feature representations, while the generated parts are not necessarily semantic. Thank you very much for your attention. Please check our webpage for code and further information, and come visit us at our CVPR poster session.